This is our next topic, two-way tables with ordinal data or interval data. So now that we've expanded our scope last time to tables which might be, instead of 2 by 2, I by j, this is 2 by 4, the distinction between a binary variable and a variable which is ordinal or interval starts to become meaningful. So if we're thinking of this thing as increasing, like in the heart disease example, where this is cholesterol and each of these columns represents an higher level of cholesterol, we'd like some techniques to deal with that take into account our knowledge that as we move to the right, this number is increasing, that there's ordinal structure to the columns, not just purely categorical structure. And we have kind of three approaches to do that. So approach number one is the one we saw last time, which was to use comparisons or effect sizes. And when we use an effect size, when we study effect sizes, we know that though there are many effects that we could measure in the table, in this case 4 choose 2, there are fewer than that degrees of freedom, right? There's only, in this case, 3 degrees of freedom. And so one strategy, the one we saw last time, is to use the effect size and match our degrees of freedom to ordinally meaningful comparisons. Right, so in other words, go this way, then go that way, then go that way, and don't do something like compare this with this minus that, and then compare in the other direction, that minus that, and then that. So something like that doesn't respect the ordinal structure of the data. Something like this does respect the ordinal structure of the data. So if we make our comparisons sort of successively, and we say, okay, your risk increases by this much when you go from this column to this column, it increases further here, increases further here, or we compare each one to the baseline, that's sort of implicitly using our knowledge of the ordinal data. Okay, so that's technique number one. But that's sort of not inherently ordinal in the sense that our measures of significance, it won't be any better than if we knew nothing about the columns, right? It just tells us that we've represented it. Another thing we can do is we can code. So we can code the columns into something numerical. Right, we can assign numbers like 1, 2, 3, 4, or say the max of these, 199, 219, and so on. So we can code these numerical things, and now we have a data set where we have some, maybe either a binary or a numerical thing here and a numerical thing here, and we sort of just pretend we're doing regression, right? So code into numerical and compute correlations and so on. Sort of do regression. And so one of the themes for this is that a useful way to think about ordinal data is just suddenly your knowledge about regression and comparing continuous variables becomes relevant again. You just have to be careful about how you apply it because there's been this discretization that's happened. And the third thing we can do is we can use sort of custom designed statistics that know only about ordinal relationships and aren't able to capture interval relationships. Right? They sort of equally space these or thinking about these purely as ranks. The nice thing about purely rank-based statistics is that if you're constructed in the right way, they're not affected by monotonic transformation. So, they're totally agnostic about, if I think of this as say cholesterol, maybe to get the best linear relationship, I should take the log, or I should subtract a constant from it, or I should do some other transformation. If I use a rank-based statistic, it just completely ignores that. It only cares about the relative rank positions of these, and is not even able to pick up what transformation. So they're invariant to transformations, which is a pretty good definition of what it means to be a rank-based statistic. Okay. The sort of bad news, though, is that many times what this actually amounts to is just using a simple encoding here, like encoding this as 1, 2, 3, 4, and then going back to this sort of correlation statistic. So while it's good and they're useful, sometimes they just amount to a particular scoring scheme for doing correlations the old-fashioned way. It's also possible to deal with partially ordered data where maybe I can say that one column is greater than another, but there are some columns which are not comparable. But we won't talk about that. It would take us too far afield. But that's possible if you need to do it. OK, so we've talked about this already. Let's zoom into this sort of coding thing. So what's the big measure of, most common measure of association if we have numerical variables? This is correlation, right? And because we have other types of correlation, let's call this Pearson correlation. So the true correlation is the covariance of two random variables, which I'm now thinking of as numerical variables for this to make sense, divided by their square roots of their variance. And we have an estimator, which is some estimated covariance of these two variables, divided by their standard errors, square root of the estimates of their variances. And just to remind you, covariance of two random variables is the expected sort of normalized product which simplifies. And you can also use this to think about the variance. Just let x equal y. So you did the difference between the mean of the two variables multiplied minus the product of the means. Mean of the products minus the product of the means. And we have an estimator for it from some data. There's an adjustment, you may remember, for correction. Xi minus x bar, the average value for x, yi minus y bar. Okay, so much is simple. Okay, so correlation, this type of correlation, of course, is a wildly popular measure of association. And I would say, in fact, it's so popular, even too popular, that many people only think about this as a way of measuring. Right? So they only can say variables are independent or they're correlated. Of course, you know that there's more than one way that variables can depend on each other. And so it's an incomplete description, but it's a pretty good description for linearly related variables of how related they are. And when x and y are Gaussian, mean and covariance and variance, so the covariance matrix, tell the whole story. In other words, completely describe the joint distribution. But for non-Gaussian variables, it's just one descriptor, which may or may not be the whole story. So if you're thinking of, if you have a bunch of points which are sort of elliptically distributed, the correlation is the slope of that line, it's a pretty good description of the relationship between the variables. But if your variables have some funny relationship like this, the correlation is not going to be a good description. So for example, you could imagine one here where the best line is that, but it's, the line may have no bearing on the actual relationship between the variables. Right? So if they're not linear related or they're not Gaussian, it's not a very good description. But when it is, they are. Okay. So the idea for this strategy is we assign some numbers up here, and we just treat them as though they were continuous things, and we compute the correlation. So again, to draw a picture, we're sort of imagining that there were some data points that really happened. What have we done? We've basically gridded up this space, sort of turned it into something interval. All these data points get concentrated at one point, which is from the coding of the row and the column. Right, so we've decided what our bins are, or maybe the bins are decided for us, and we sort of encode all these points as that value. Of course, that's going to introduce some error into our calculation. But if our point grids are sort of small and this is sort of random, you can imagine that it will get close to the same answer as I would have gotten before doing the discretization. So that's kind of what we're doing. OK, so what we need to do is we need to assign numbers to each. And there's some art to this, right? So there's sort of a default thing to do, which is to use the ranks, which we'll talk about. But depending on the question and depending on your knowledge of the data, there might be some better ways to encode the values into the columns to compute this correlation. And of course, it has familiar properties like, it's 1 with perfect association, it's -1 with perfect negative association, and it's somewhere in between in other cases, although, danger, it can be 0 even for two variables that are completely dependent on each other if their dependence is not linear. Okay, so being 0 certainly does not mean that those two variables are independent. That's only true if they're Gaussian. Okay? And so the other thing to note is that it's, of course, scale dependent. Right? I mean, we're talking about choice of encoding, but if I change the encoding, if I change the numbers, if I rescale one of these axes, I can get a wildly different correlation. So you have to be careful about that. And both variables, these are sort of assumptions to worry about. Both variables should be ordinal. And a binary is OK if you're thinking about success or failure or something. Or even better is if they're interval, it makes more sense, right? And in order for this kind of approximation to work, this gridding, we want the cell sizes to be large. Of course, what large means is not always. Because what we're doing is kind of a discretized regression. And as long as our cell sizes are big, that sort of works. And if our cell sizes are too small, it might introduce a lot of movement in the data. OK. So that's the Pearson one. And we'll maybe talk about some examples. A rank version, a purely rank version of correlation is something called Spearman's row. And the idea for Spearman's row is that we can have a situation where two variables are related and related monotonically, but the relationship is not linear. Right? And in ordinal data or in categorical data, the linear assumption is probably too strong because why are we even using ordinal data instead of doing regression in the first place? And so it's very often that we want to use something that's more like this. So the goal is to pick up monotonic relationships in the data instead of linear. So whereas the other one was linear, we're just trying to pick up that. So in other words, if I have some crazy function where this is x and this is y, and I don't know, it's like that or something, right? And it's very tight around some curve, like that. if I try to do a regular correlation, a Pearson correlation, I have to draw the line through that. And that will pick up a correlation, but it'll be weaker. This one will be able to tell, oh, this was actually a perfect correlation. It's just that it wasn't linear. So for variables which are monotonically but not linearly related, Spearman's rho will be higher than the Pearson correlation. And as a consequence, it's also less sensitive to outliers. Right, one of the classic regression stories, I have a bunch of stuff down here, and I have some point out there, and suddenly I pick up a huge correlation, but it was just one point. And because this Pearson, or the Spearman approach just looks at the rank, it can't tell that this point is here versus here. And so it won't create a spurious correlation if there's some crazy outlier. Because to the Spearman rho, which is going to pass through a rank transformation, a point being here and a point being just at the top boundary of that is totally indistinguishable. Okay, so how do you compute this? It's Pearson. I'm about to erase Pearson, but we'll replace it with Spearman. We just convert to ranks. We pick a particular encoding, and then we do Pearson. So I convert my data to ranks. What do I mean by that? So suppose I have some data, 1.5, 3.1. For a second now, let's think about, think of our observations as being continuous, not chunked, not interval. So I measured, I don't know, cholesterol or some other level in the dependent variable or independent variable, and I get just numbers, real numbers, 1.5, 3.1, 11, 4. To convert them to ranks, I make the smallest one, I get code the smallest one as 1. The next smallest one is 2. This next smallest one after that as 3, and the largest one is 4. So you can see that that's why, this thing, instead of becoming 11 or 100, just becomes the highest rank. So we convert it to ranks, and then we compute the Pearson correlation of these rank transformed values. So there's one funny thing that can happen. So what happens if I have ties? Suppose my data was 0, 1.1, 1.1, 1.1, 3.2, and 4.7. Then the encoding that I use is this one still gets rank 1. These get their average rank. So these were ranks 1, 2, and 3 in no particular, 2, 3, and 4. 2, 3, and 4 in no particular order. I assign to them the average rank that's among them, so they all get rank 3 when I plug them into Pearson correlation. And then this gets rank 5, and this gets rank 6. So in true continuous data, of course, ties would be rare. In the categorical setting, of course, this is going to be common, right? Because we've already grouped our data, right? We don't know cholesterol between 0 and 199. We've grouped it all into 1. So that's like saying we're going to treat everyone who's in that group as a tie. And if we wanted to do this, assign to them the same rank. Right? So implicitly, when we have a table like the cholesterol table, and we have some quantities up here, 0 to 199, whatever it was, 200 to 219, and we have some counts here. What we're saying is that everyone in this column, although they had some true value, we're treating it as though it was all the same rank, and that rank is 1. so on. Okay. So we're sort of implicitly doing this when we encode these numbers as just 1, 2, 3, 4. Okay, so this is this procedure, the Spearman is sort of a natively ranked or natively rank-based procedure, even though it's secretly just Pearson with some encoding. And so it works great if the data is just, or it makes a lot of sense if the data is already just ordinal to begin with. Ordinal is all we know, right? We just have that this is bigger than that, this is bigger than that, and that's bigger than that. Then it makes sense to do this because we don't have any other better way to assign numbers. And it also works well for when we don't want to think about whether we've chosen the right transformation. So it has a simplified formula. So if I think about outcomes, I have two random variables. And I have outcome xi and outcome yi. And I assign to them a rank xi and yi. I could compute a difference of ranks. So this is like a number, a real number. And this is that rank. So this would be like the 1.5, 3.1. This would be the 1, 2. And for each observation, it has an x value and a y value, and I could subtract the ranks. Now these observations are not visible directly in the contingency table, right? These are the rows in the data frame. These are the actual, index. I is the index of the person. I goes from 1 up to n, the sample size. And if you have that, then you can compute rho, Spearman's rho, as 1 minus 6 times the sum of these di squared divided by n squared minus 1. And if you only have the table, of course, the data is all there. And you should think about how you compute this number just from the table. So you can still do it, right? All the data is there, even though you don't have the explicit observations. And I think that's one of the exercises for you. There's also code that's on the website. But.
So that's 1 minus 6 sum of di squared? Is that
Yeah.
Is that just from
the one you're saying is the one out in front, the one should be, sorry.
Oh, I think he's wondering what that is before the sum.
It's a 6,
It
yeah.
is a 6, okay.
Yeah.
Is it always 6?
Yeah, it's just an algebra. If you write it out by hand for some small example, you'll see that that's what it works out to be. Okay, so in regression, right, we have like an R squared measure of effect size, and we'd like here to have some kind of hypothesis test. Yeah.
So we have x and y as the variables on the table, then wouldn't that imply that the table is always square that we're looking at? Since the di is xi minus yi. What happens if
Well, no, it's like, so like yi might only be this, so like x might only be 1 or 2, and y might be 1, 2, 3, 4, or little one actually. Right. So this would be 1 and 2 in our example, and this would be 1, 2, 3, 4. And the true values for this would be, the thing that gets assigned 1 is some number like 102, which is between 0 and 199. That gets assigned a 1. 202 gets assigned a 2. And so on. And this one gets coded just by disease or not disease. So 2 is disease and 1 is not disease.
Okay, what is that? Because di is xi minus yi, but there's more values for yi than there is xi. There's only 1 and 2 for x, and 1, 2, 3, 4 for
Yeah.
y.
It'll still work. We're squaring it stuff, so it's not going to ever.
Just like what happens when we get to yi is 3, since that's when.
There's no one for xi.
So like, we'll get 2 minus 3 is -1. Then it gets squared into the sum.
How do you
Yeah.
know to use 2 when it's 3 and use 2 when it's 4 also?
Well, aren't they like grouped together kind of?
Can you do the example? Like that doesn't seem. I don't think I can do the calculation.
Sure. Well, here, let me do it this way. So suppose I have 1, 2, 3, 4, 1, 2. So each data point is just a point on this chart. If it was a true data point, right? So like, suppose this is the heart disease. So this is maybe this is healthy and this is disease, and these are best cholesterol levels. Right? 0 to 199, 200 to 219, and so on. Before the data got compressed into the columns, it looked like, okay, this person got disease, and you can think about this being as continuous. Maybe it was here, right? And then this person didn't get disease, and it was here. And this person didn't get disease, and it was here. So that the numbers look kind of like smooth sets of points like this along each of these lines. Then they got grouped into the data, into the columns. So everything that was in this 0 to 199 block got concentrated into that spot right there. Right, so a single person who had disease and had cholesterol 102 becomes that point. Another person that has disease and cholesterol 150 becomes another point there. So there's some buildup of points there. And there's some buildup of points in each of these, which are just the table entries. Okay. And then, so now I end up with some data, with just a bunch of multiplied points here. And this is 23, this is 45. And in other words, there's 45 dots all at the same spot, which were originally spread out. Then I take that data and I draw the best fit line through it. And that's my row. And the fact that it works out to this is just, you just think about that as an accident of, if you compute that number, that's what you'll get. That's the claim.
But that order doesn't have anything for the cell size, like 23, 45. Where
Right. Because this sum, I equals 1 to n, and n is equal to the sum of all these numbers, 23 plus 45 plus.
Oh, okay.
So this formula is treating it as though you had the data frame, which just lists each individual as its own row, or the table of the data, whereas this is the summary of the data.
So the n on the bottom is the total n?
Yeah. Sorry, so this should be lowercase n, I guess. Yeah. So it's kind of, when you think about it this way, it's like you're just writing the table on the chart and drawing a line through it. It seems kind of ridiculous that it works, but it's fine. It works, makes sense. And so there's this sort of, again, there's this kind of like discretization. Like there was some real spread of things, and we sent them all to that point. There was some real spread of things, we sent them all to one point and counted them as being one thing. And as long as those balls are sort of accurately centered, it won't be too different from the answer we would get from Pearson.
Point, the D of that 23 point would be 2 minus 1.
Yeah, right. Right, it would be 2 minus 1, but it would appear 23 times in this sum.
And we do the same thing for every 8 point, right?
Yeah, so each of these points would appear. So this one would be 2 minus 3 appearing 45 times and so on. Yeah.
Thank you.
Okay, so our test statistics is this thing called the Mantle Hansel test statistic. And this is going to be a test statistic for a hypothesis test, where the null hypothesis is that the ordinal variables are uncorrelated, by which we mean exactly just, Spearman or Pearson rho is equal to 0. And the alternative hypothesis is that rho is non-zero. So it's two-sided. And again, especially in the case of Pearson, rho being non-zero, or rho being 0 does not necessarily mean they're independent. It just means what it says, that rho is 0. So this test statistic is just n minus 1 times r squared, where r is the sample correlation. Pretty simple statistic. So I should say that, although you should use R and SAS or whatever to do this stuff, a lot of what we've talked about, almost everything we've talked about so far, you can do by hand. The only thing you need the computer for is to look up the table of chi-squareds and normal random variance. So everything we could do, so almost everything we've talked about, you could do with a calculator and a table of chi-squared and normal. There's no exception. So if you get stuck on the software, you can always just break out a calculator. When I'm doing this stuff, I often just use a calculator, because if you don't need to get into the software, you don't bother. Okay, so this is the, and then one can show that under the null of rho equals 0, that m squared is approximately chi-squared with 1 degree of freedom. So it'll increase as we increase the size of the sample, or we increase the effect, our significance will increase. Okay, so so what's the point? So we already have goodness of fit tests, hypothesis tests for independence. So a goodness of fit test for the independence model is the same thing as a hypothesis test for independence. Namely, the Pearson x squared or chi-squared and the deviance, right? So why would we use this m squared instead? Or what benefit will we sort of hope to get? Think about that for a second. So the idea is that because of the way we constructed it, m squared is aware of the higher hypothesis about the ordinal nature of the data, right? We're asking a very specific question. We're saying not are these related or not, but just are they linearly related after this transformation, right? Do they have this particular relationship? And so since it's a more specific thing, it has more statistical power. So it can reject the null more easily because it's considering fewer alternative hypotheses. Or fewer ways to fail. And our precise way of saying that is in terms of degrees of freedom. So the m squared just has 1 degree of freedom. Well, it's rho, basically. Right, so our null hypothesis is that rho is equal to 0. Our alternative hypothesis is that rho is not equal to 0. So the only way in which we can fail, from the perspective of this model, the only way in which we fail to be independent is that rho has this 1 parameter of deviation. That's our 1 degree of freedom. Whereas in the general independence model for an I by j table, there's I minus 1, j minus 1 times j minus 1 ways to fail. Right? There's many more directions we can go. Right? With all these odds ratios, as all those odds ratios go away from 0, those are all the different ways we can fail to be independent. Here we're saying we only care about one particular way to fail to be independent, which is that this rho deviates from 0. So that's what's going on. So we have, in that sense, we have fewer alternative hypotheses. This has only 1 degree of freedom, which is basically measured by rho instead of by all these odds ratios. And that's compared to the I minus 1, j minus 1 degrees of freedom for the Pearson test or the deviance test. And yet, the value, the numerical value, is approximately the same. So the number that I get for m squared will be close to the number that I get for the Pearson chi-squared or for the g-squared test. But because the degrees of freedom here is only 1 versus a much higher degrees of freedom here, that same value will be far more significant as a 1 parameter test. Right, so we're saying we're sort of taking all of the ways to fail, compressing it into 1, and that's why we get more power. We get more data per degree of freedom, and that means more statistical power. Okay, so for this, well, in the Spearman case, we have only one encoding of the scores, and so there's nothing to think about. But in the Pearson case, we need to think about and here there are some scores. So how do we assign a number to each of the entries of the table, right? Should we use 1, 2, 3, 4, or should we use 1, 10, 100, 1,000, or what, right? And of course, this is going to be something of an art. There's defaults. The defaults in R and SAS are just to use integer values, so essentially to do Spearman. It's also called equal spacing. So it will just use 1, 2, 3, 4, or 0, 1, 2, 3, if you don't tell it anything else. And there's a function, as we talked about, I think, on the first day with the R notebook, to assign these numbers. So you can, if you have particular numbers that you would like to assign, you can do that. And of course, different choices will give different Pearson coefficients. So let me concretely look at the heart disease example and just go through the most common. Sometimes cholesterol choices. So we had again 0 to 199, 200 to 219, 220 to 259, and 260 plus. I don't care so much about the. Okay, so the numbers in each of these things. So I'm going to ignore how many got disease and how many didn't, because for this purpose, I just want to think about the total. So there was 319 of these. There was 254 subjects in this range, 470 in this range, and 286 in this range. So the equal space or integer coding would just assign, okay, 1, 2, 3, 4, or 0, 1, 2, 3, or Spearman coding. I could do midpoints. So if I know where I know the numerical numbers, the numerical values of my original data, these numbers here, I could use those to assign a number. So halfway between 0 and 199 is 99.5. Halfway between 200 and 219 is 209.5. Halfway between 220 and 259 is 239.5. And up here, well, I don't know, right? Because I don't really know how high it went. So either I would say maybe 260, or I would just pick some number based on my knowledge of the data, right? But here we don't really know. Okay. So maybe it's not the best choice here. But this kind of choice of midpoints makes the most sense if you think that your data is truly interval. That is, that the differences here are meaningful, and you want to preserve some of that, right? This is saying that in this discretization, you had a spray of points, and you blocked them into categories, and you want to assign all the points in a particular range to the center point of that range. The other thing we could do is something called mid-rank. So this ignores the values that were given from the experiment and constructs something which is based on the rank. So the idea here is, okay, imagine that instead of having this table, I had the full list. I had the full list of all of the subjects, right? Big long list of however many thousand people. And I ranked all of those people based on their cholesterol, 1 through 1,300, whatever the total is, right? And then for each group, I just chose the midpoint of the rank. So that means that in this category, there are 319 people, and they're ranked 1, 2, 3, 4, and so on, up to 319. So their midpoint is half of this. Well, okay, so if they were ranked 1, 2, 3, their midpoint will be 2. So if there's an odd number, I'm going to get just the number in the middle. If there's an even number, I'm going to get 2.5. And I'm going to assign the same rank to all of them. Because I don't know what their actual rank was. So it's like they tied. So here, instead of 319, I'm going to put 319 plus 1 divided by 2, which is 160. Right, that's the kind of middle rank for people. So I'm just pretending that everyone in this category gets the rank 160. Similarly, everyone in this category, these are ranked 320 up to 573. And in the middle, I get 446. There's an even number, so I'm going to get a decimal. 446.5 is the midpoint of these ranks. Well, there's 2 in the middle, 446 and 447. I just take the one in between. I assign to everyone in this group, all these 254 people, that rank. So these look like interval numbers, but they're not. They're just ranks, right? Just that we have a lot of subjects. And so on for this group. They're ranked 574 up to whatever, and their midpoint rank is 808.5. 0.5 because this is an even number. And then the last group will get rank 1186.5. Okay, so that's the mid-rank. And there's automatic functions to compute that for you if you don't want to go through that. So that's another sensible choice that people use. And if you don't like any of those choices, of course, you're free to choose whatever ranking you like, as long as you can justify it or you explain why it makes sense for your particular data. So is that clear? And hey, they're not always so different. So in this data, for example, if I use the mid-rank encoding, I get an m squared of 27.84. If I use an equal spacing integer encoding Spearman, I get an m squared of 26.15. So you can mess around with different encodings and see how well they capture the situation. questions about that before I go on to the next topic?
The pure state oral is actually same with the equal size.
That's right. Or Spearman, yeah. Slightly differently justified, but the same answer, yeah.
What is, so like when the n squared equals 27.84, what's like our interpretation?
Well, you should think about that as compared to a chi-square with 1 degree of freedom. So that's very significant. And it's higher, I don't remember what it was, but if you look at the ones from when we just did a measure of independence, we didn't get as strong a relationship. Right, so the failure of independence was also strong, but it wasn't that strong. Like, that's a very high number for a chi-square with 1 degree of freedom. So what that's showing you is that it's a lot easier to find significance should you, if you use this type of test. I thought I had this earlier calculated, but maybe not. Anyway, you'll get more power. You'll get more significance for the same question. Okay, so the next topic is dependent samples. So for two-way tables. So if you remember, and this means that we essentially have a new type of sampling assumption. So if you remember that one of the ways our sampling assumptions could fail in two-way tables, for example, in the example where we poll a bunch of households and we ask two people in the same household, and that's that's bad for our binomial assumption, right? Because we fail in independence. Well, that means we need another sampling assumption that will make sense for that situation. Another way to say it is that perhaps we're most interested in such a matchup, right? We're actually interested in that, and the best way, a good example of that is like longitudinal studies. And again, we're going to have a situation where we get more statistical power. So the typical example is we have something like we have two different times, time 1 and time 2. And we have two possibilities. We have a prospective study. In prospective study, what we do is at time 1, we choose a group, right? Treatment or control. And at time 2, we observe the outcome. This is like the heart disease study. The other thing we could do is dependent. We could look for a change, right? So we could like observe an outcome here. Outcome maybe healthy versus disease. And then we could observe the same outcome again on the same subjects. And we would want to do a different kind of inference about this, right? Because there's there's potential for great dependence between these. And the kind of question we would want to ask is something like, how does this state change? Are people becoming sicker or healthier over time? Maybe there's some outside factor, something that happened in between to this group, right? And we want to know, how do they change over time? And so by looking at the same object twice, we get a gain in power. And we get different measures and different hypothesis tests. So the other classic example, which is the example I note, is it's like a poll for presidential approval. So we ask 1,600 people before and after some event or some speech or something. Yeah, something bad happens. Okay, so then we get a table of times, time 1 and time 2. And we have people that approve, people that disapprove. And we're asking the same people twice. We're calling them back. And we get some totals. 794, 150, 86, 570, 944, 656, 880, 720, some total number, grand total of 1,600. So what question do we want to ask of this table? Well, we could ask, are they independent? But that's kind of a silly question to ask, right? So we could ask, okay, using the tools we already have, we could say, okay, are they independent? Well, that doesn't make much sense. We know they're not independent because it's the same person being asked more than once. And this off diagonal term, if I multiply this times this divided by that times that, of course the number's going to be huge. Well, no, very not independent. That doesn't surprise anyone. That's not really the question we want to know. So that's, what's this going to be? A chi-squared of 788.3. 1 degree of freedom. Okay, not very far from independent. Opinions haven't changed very much. What we really want to do, right, so this was really a presidential polling firm. We want to look at the margins. What is the percent approval rating, right? So 59% approved before the speech and after 55% approved. So there was apparently a 4% drop in the president's approval rating. Right, this is the sort of thing that keeps presidents up at night. And our question should be, is this change significant? And what kind of change is this? This is a difference of proportions. Right, this says that if I talk to 25 people, I should expect to see, one person change, something like that. So what we want to know is, do the margins change? The margins of the table, marginal proportions. From time 1 to time 2. And so the relevant test, as that suggests, is a test of marginal homogeneity. And the test we're using for that is something called McNemar's test. So what is the null hypothesis? The null hypothesis is not independence. It has nothing to do with independence, right? We know for sure it's not independent. The null hypothesis is that marginal proportions are the same. And since the number is fixed at 1600, then the margins are the same. So if I think about it this way, I can write P11, P12, P21, P22. That's my table. My margins are P1 plus, P2 plus, P plus 1, and P plus 2. So I'm interested if this number changed, right, in 2 by 2 tables. If there were more than 2 by 2, there'd be more categories. But for this, I want to know if this number changed. This number is just equal to this plus that. This, and I want to know, this is the after. This is the before, this is the after. That's equal to this plus that. They share in common this number. So the only difference is, the only thing I really want to know is whether these two numbers are different or not. So P1 plus minus P plus 1, the difference of proportions